Hello, everyone. Welcome to what I believe is the last week of your online lab. We'll be going over two lessons this week, both infrared spectroscopy and NMR, or nuclear magnetic resonance spectroscopy. And this first presentation will only be on IR. You'll have a separate presentation. Each of them are going to be a little bit longer than your normal presentations. There's a lot of material to cover, and I'm really not sure how Dr. Mighty is going to go about the quizzes and pre-lab quizzes and post-lab quizzes, the questions you're going to get. So it would behoove you to, of course, look at these, look at your book, and use online resources because as the TAs, we really have no idea what's going to go on with questions here. So without further ado, let's go into IR spectroscopy. Okay, so there are four main ways of using instrumental methods for determining the structure of molecules. The four main ways. There's quite a bit more that require high energy, like X-rays, but we're only going to be talking about the fairly standard dye systems. The easiest to discuss and go over would be number 2 and 4, the IR and the ultraviolet. And then a little bit further in depth would be your NMR and your mass spectroscopy. Also, in terms of those, your IR and your UV instruments are going to be less involved and cheaper to purchase and maintain, whereas your NMR and mass specs require quite a bit more room, money, maintain, and upkeep is quite a large percentage of their costs. So we'll be focusing in this discussion about IR, which most people should know as basically infrared waves are basically how our body senses heat. It's just a lower energy than your visible light. And all it does is when it hits molecules, it causes those molecules to vibrate. And that vibration, our body and our brain senses that as heat. Now we can use these vibrations and these wavelengths of light to determine different things, because you can basically think of molecules as very simplistically as a classical physical mechanic ball and spring system, where you have a bond is a spring and the atoms that are bonded together are the balls on the spring, and you have a spring constant that determines how easily that spring is compressed and can relax back to a standard state. And you can do basic calculations on that, and they're fairly close. You get a lot more in depth into it if you want to get really statistical and accurate about it. But it's a good model to go with, and that's the basis of the model we'll be talking about for IR. So IR is dealing with the interaction of infrared radiation with matter. So if you look at IR spectrum, basically this is going to provide chemical nature, molecular structure. In terms of what you've learned so far, it's going to be able to tell you functionalization, functional groups that are found on a molecule. Because each functional group has a different polarity or electron density, causing different stretching and bending and shaking of the molecule at certain IR modes. And this can be determined by the IR instrument and read out, and that'll give you an idea of what you have in terms of your molecule. So generally, the most common thing, you measure the absorption of IR radiation. There is reflection and emission technology. Those are a little bit more advanced, a little bit more specific, but the standard absorption technology is what most benchtop IR machines use. And this is very, very widely applied in organic as well as inorganic molecules, and especially organic molecule compounds, organometallic compounds. Basically, every branch of chemistry at some point or other will be using an IR just to make sure functional groups are going on, to see different vibrational modes, transitional state information, stuff like that. So it's a very, very, very commonly used instrument. Basically, every research lab either has one in their lab or uses one, in coordination with another lab, very, very consistently. And they're not, in grand scheme of things, they're not very expensive, so it's widely used. So talking a little bit about IR, it's just a form of EM radiation, electromagnetic radiation. And these radiation packets, they're known as photons. It's just a discrete bundled packet of energy of a specific wavelength. They both have wave and particle duality, meaning they can act both as a wave and a particle. They have mass, they interact like particles, but they also can go through quantum wave functions and collapse on themselves. They can move about in nature as a wave as well as a particle at the same time. So there's a whole bunch of quantum interactions that if any of you take any quantum physics or quantum chemistry, you'll learn a lot about. But other than they do it, that's really all you have to know about for this type of information. So, like I said, a photon is basically what you can consider a particle of EM radiation, even though that's not a really good word for it. It's just a packet. It's a discretely bundled packet. I say discrete because these are quantum systems, and quantum, you hear that thrown around a lot. You hear it in commercials labeled on stupid things, but all quantum is a discrete energy. A quantum state is a state that has the exact energy every single time. That's all quantum means. It doesn't mean small or mysterious. It means it has a quantized integer value energy level at all times. So a 200 nanometer wavelength of light will have the exact same energy every single time, no matter its source, no matter what it goes through, whatever. It's always going to have the energy. It's quantized, always. That's what quantum means. So in terms of EM radiation, we characterize these by wavelength and frequency. Wavelength, we use the little lambda symbol, and frequency, we use the nu symbol. It looks like a V. It's sometimes a little curly on the front of it. But the wavelength is, if you're graphing this wave, they're all sinusoidal waves, so they have periods. So if you're graphing it from one point of the wave to the next exact point of the wave, once graphed, that's the wavelength, the distance. It's a distance. And frequency is the number of times that wave passes a specific set of area or period on this graph. Frequency is wavelength before is everything's metric, of course, so it's measured technically in meters, but what we do most of the time is we use nanometers because nanometers is mainly what we're going to be seeing for visible light. And since visible light is the way we perceive everything in the universe, that's what we kind of go with as a standard. So, your visible range is anywhere from, say, 250 to 750 in that range, plus or minus a little bit here or there. So we use nanometers. For frequency, we use hertz or inverse seconds. It's the same thing. 1 inverse second is equal to 1 hertz. That's just what we call it. And you can think about it as in 1 second, it basically, that wave oscillates a certain amount of time in 1 second. That's what the frequency is, the number of oscillations per second. So energy of these photons or these waves is directly proportional to frequency and inversely proportional to wavelength. So basically what you can say is energy is equal to your frequency times a universal constant, which we're going to call H, is Planck's constant. And Planck's constant, you see it all throughout physics and chemistry. It's basically a way to account for the interaction of waves and or particles throughout the matter and permittivity of a vacuum, how they interact things, how they bounce off things, take energy from the environment, stuff like that. And the actual value for Planck's constant, like I said, is constant, so it's 6.636 times 10 to the negative 34 joule seconds. So it's a crazy value. If you're an actual chemist or physicist, you use it so often that you have it memorized. I was able to just spit it off at the top of my head. So that's something you might be, if you need to use it in a calculation for something, it's very easy to look up. It's a very, very well-known constant, but that's what you will be needing to use for calculations and stuff like that. Here we have just a simple little characterization of the EM spectrum and the types of energy that's involved with each specific wavelength, frequency versus wavelength, energy, etc. You can see right in the middle of the green, that's where our visible spectrum is. And it's 10 to the negative 4 centimeters in terms of visible wavelengths, and that's going to be in the sub 1,000 nanometers when you do the calculations to change for that. And if you notice, if you go down from visible, you get IR, microwave, and radio. Those are all lower in energy, and they have a higher wavelength. So, like we said, energy is equal to frequency times a constant. It's inversely proportional to the wavelength. So the way you think about it is, if you have a wave and the wave is really long and it takes a long time to go from period to period, that's going to have a lower energy. But if in the same time period it hits that period 3 or 4 times, if it's got a really short wavelength, that means it's vibrating a lot quicker. There's more energy involved with it. So the way you think about it is, energy is always proportional to the frequency, and frequency and wavelength are inversely proportional to each other. So the higher the frequency, the higher the energy. The higher the wavelength, the lower the energy. That's just any way you can think about that. That's just a simple mathematical relationship between the two. So, like we said, IR, microwave, and radio are all lower in energy, whereas UV, X-ray, and gamma ray are all higher in energy than your standard visible light, with gamma ray being the highest and radio wave being the lowest. Now, in terms of just the really incredibly high energy, we just all lump those into gamma rays because there's basically no top end of the scale. It just keeps going and going into the the most energetic systems we see in the universe. And it's the same with radio. Once you hit about 100 or so meters of wavelength, then you talk about radio waves is really, really low energy, and it just keeps going and going and going. There's really no end. It's just all lumped into the radio waves. Now, the thing to think about here is, and to see is, if you notice for the IR, that has molecular effects. It's got molecular vibrations. So when you hit a molecule with an IR wavelength of energy or light, it induces vibrations into that molecule. UV, which is higher energy, also has a molecular effect, but that induces electronic transitions. That excites electrons into higher energy states and allows basically for chemistry to be done. So IR is basically just, it doesn't change the molecule at all. It just causes the molecule to vibrate, rotate, translate, move around. Whereas UV starts to actually inherently change the composition of the molecule by exciting electrons, making transitions, sometimes even being able to break bonds or create bonds, depending on how things go. Now, if we go even higher to X-rays, then you start getting ionization. The X-rays are powerful enough where they start hitting electrons and even the nucleus of the atom and start ejecting particles from the atom itself, making ions where you fully lose electrons. And the thing here, UV, you don't lose those electrons. They just become higher energy, and then they can slowly relax down and do things. But X-rays, it actually ejects that type of things. And with microwave, it's lower than IR, so it doesn't cause vibrations, but it causes rotations. And that's how all of your at-home microwave works. They have a microwave generator inside of the microwave, and it is specifically keyed to eject microwaves at the exact wavelength that will excite water molecules. And it causes basically water molecules to flip and rotate constantly. And that constant rotation increases the energy of the system and causes things to cook from the inside out. That's why you're able to thaw things and stuff like that in the microwave, and it's a pretty even cook. That's also why the edges of certain, like if you heat up meat or something like that, the edges are always a lot harder because there's more surface area to the edge. That water starts to rotate, heat up, and can evaporate. So it basically desiccates the edges of things. That's how that works. And at the very bottom is the radio, and that's nuclear spin transitions, and that's what we're going to be talking about the next lecture, the NMR. You use a high radio frequency generator to cause all the nuclei to spin in the same direction, and you can really hit it with an orthogonal wave and cause it to relax and measure the time. But like I said, this one is basically all going to be about IR. Here we have another very textbooky way to look at the IR spectrum, the EM spectrum. This is more, I guess a good way to say it, this is more to scale. And if you notice the visible light range, the light range we see that everyone is basically able to see is anywhere from 400 to 750. Some people can see down to 250. Some people can see a little bit over around 800, maybe 900, but that's the standard 4 to 750. That's a pretty standard range. And it's a very, very, very small range of these EM spectrum, if you notice, because this goes all the way, from thousands of meters wavelength down to, 10 to the negative 20 in terms of gamma rays really, really small. So the reason we're only able to see that is pretty simple. We're only able to see visible light because our sun, the source of our natural light, where the everything on Earth evolved, is 96% visible light output. So since that's was our biggest source of light, that's what our eyes are capable of seeing. The sun does output about 4% ultraviolet, and then the rest is you get some X-rays out of it, very few. And then of course there's always infrared associated with it from the heat coming from the sun. But this is just another simple IR picture for you. Here we have some dreaded mathematical representations for you. Everyone loves the math. This is more talking about basically that the energy is proportional to wavelength. The energy is proportional to frequency and indirectly proportional to wavelength. So we can start out by saying the speed of light, or c, which is 3 times 10 to the 8th meters per second, is equal to the wavelength of a photon times its frequency, always. So you multiply its wavelength and its frequency, you'll always get the speed of light. So that's a constant. So we can use that for mathematical representations. Then we also say, like we said earlier, the energy of that photon is always equal to Planck's constant times its frequency. Pretty simple, straightforward. So we can use those two we just talked about and rearrange and substitute. So we can substitute energy equal to h, Planck's constant, and then we can change the frequency into a wavelength ratio by looking at the original statement of wavelength times frequency equals c. So you just rearrange, plug it in. So you can say energy is equal to Planck's constant times the speed of light divided by the wavelength. So if you only have the frequency or if you only have the wavelength, you're still able to determine energy either way, just by using some simple manipulation. And here's just a graphical representation of the periodic nature of a wave, where the wavelength, for instance, in between those two arrows, the wavelength is the trough to the exact point on the other trough. That would be the wavelength. The frequency is how fast that wave hits, peak to peak or trough to trough in a certain period. C, of course, speed of light. E is energy, or kinetic energy more specifically. That's what we're dealing with here. And of course, H would be Planck's constant, 6.636 times 10 to the negative 34 joule seconds. Okay, so dialing a little bit more into the actual IR radiation. So for IR, the wavelengths we're talking about is anywhere from 2.5 to about 17 micrometers. That's what the little u stands for, micrometers. And the frequency of those are anywhere from 4,000 to 600 inverse centimeters. You'll see inverse centimeters a lot in spectroscopy. You'll also see inverse centimeters called wave numbers. It's the same thing. So basically, you just took your value, divide it by 1, and that's your inverse. Change it to centimeters, of course, and that's your wave numbers or inverse centimeters. You'll see that a lot, and it's just an old way of doing it. Most of these things are going to be in nanometers. Infrared can move into the centimeter range, but don't be confused if you see inverse centimeters or wave numbers. It's inverse centimeter. One inverse centimeter is one wave number. So the interesting thing here is those frequencies, that frequency range, those match exactly the stretching and bending vibration energies that molecules have for stretching bonds, bending bonds, stuff like that. And what IR spectroscopy does is it irradiates your molecule in question with a broad spectrum of IR radiation, and depending on the frequencies of the bonds in that molecule, it'll either absorb or transmit the radiation. If it matches the bond strength frequency, that IR radiation will be absorbed, the bond will be stretched and vibrate. If it doesn't match, that the IR radiation will pass through the molecule and be detected on the other end. That's just the very basic, simplistic way of looking at IR. If the radiation that hits your molecule matches the bond frequency, it's absorbed. If it doesn't match, it's transmitted. And it's just a simple absorption versus transmission graph that you get at the very end. So by using these, then the key thing here is covalent bonds, where that's what it measures. If you put just a basic non-organic salt in there or something like that, you're not going to see any IR, because we're talking about ionic bonds. These are covalent bonds. We need an actual physical bond for these to be used. So using IR, you're able to tell, if they're covalent, of course, what types of bonds are present, and you actually will be able to get some structural information based on where on the IR spectrum that your output is coming. And we'll talk about that here in a second. Okay, so even more math, yay for you. We're going to be talking about the stretching frequencies of two bonded atoms. So we need some mathematical way of determining this, and the instrument needs some mathematical way of determining it. So we said earlier that energy is equal to Planck's constant times the classical frequency of your photon. So what we're going to do is we're going to change that around a little bit using classical mechanics with a ball and spring system. We can use something called Hooke's law, which has a K value, which is the spring constant, and that little lowercase Greek u, that is what we're going to use for something called reduced mass. Now, of course, frequency basically is what you're going to key back to the energy of the system. It's the how many times in a specific time period that the wave oscillates. It's also inverse to the wavelength. K, as I said, is called a spring constant. It's a good way to determine how stiff a spring is. The higher the constant, the harder it is to compress that string. And then, of course, the underscore U is the reduced mass. And that's basically the equivalent of the mass of the largest atom. As far as I know, you will probably not be asked how to determine the reduced mass, but there's just a simple formula for it, determining two different the reduced mass of two different specific atoms. You can look it up if you need to, but all it does is basically it gives you a quick way of finding the center of mass of two objects. So if you have a heavy, say you have a bowling ball, a 12-pound bowling ball, and then you have a 9-pound bowling ball. If those are held together by a spring, the center of mass is going to be closer to that 12-pound bowling ball than it is the 9. And the reduced mass formula basically tells you about what percentage of distance between the center of that bond, the center of mass is going to be. It's just simple calculation, nothing to really worry about. So the thing to see here, of course, is V, your frequency, is going to be directly proportional to the strength of the bond between your atoms. And it's going to be inversely proportional to the reduced mass. You can tell this direction. Anytime you have an equivalency sign, you've got your frequency on one side and your K and your reduced mass on the other. If both of them are in the numerator, they're going to be directly proportional. If one's the numerator, one's the denominator, they're going to be inversely proportional. That's the way it works. So just like frequency was directly proportional to energy, frequency is also directly proportional to the strength of the bond. Therefore, energy is also proportional to the strength of the bond. And whereas frequency is inversely proportional to the reduced mass, you can say the same thing with energy. It's inversely proportional to reduced mass as well. Here's some more basic extrapolation of theory here. Here's some specific stretching frequencies for some bonds, and the energy found in those bonds, the kilocalories or kilojoules of energy required to make those bonds, and then the stretching frequency of the IR energy in wave numbers, again the inverse centimeters required to cause those bonds to start stretching and vibrating. So if you notice up on the top here, we've got a carbon-hydrogen bond, a carbon-deuterium bond, and if you haven't heard of deuterium, deuterium is just a hydrogen molecule with an extra neutron in it. It's basically, if you ever heard of heavy water or deuterated water, that's what it is, just deuterium. And it's a good marker for NMR and some other radioscopic techniques. So you'll see it a lot. And then of course the carbon-carbon bond. And if you notice, as the atom attached to your carbon gets heavier, the bond energy actually goes down. There's really no difference between hydrogen and deuterium. They're very, very similar in mass. But if you look at the difference between the carbon-hydrogen bond and the carbon-carbon bond, there's a fairly decent drop in the frequency of the bond energy. But it's the same thing happens because, like we're talking about, energy and frequency are proportional. You'll notice as the atoms get heavier, the stretching frequency decreases. It's the same thing. So if your bond energy is going to be decreasing, the stretching energy also decreases. And one way you can think about this, if you look at the differences in these frequencies and bond energies, is you can think about it as the more energy it takes to stretch that bond, the higher the bond energy is going to be. So if you look at the CH bond, it takes 300 wave numbers to stretch the bond. Therefore, it's higher than if you notice the 1200 it takes to stretch the CC bond. Conversely, if you look at the bottom, we've got a carbon-carbon single, carbon-carbon double, carbon-carbon triple bond. And if you know anything about those bonds, the carbon-carbon bond is a longer bond. Carbon-carbon bond double bond is shorter, triple bond is the shortest. And the triple bond is much stronger than a double, which is much stronger than a single. It takes more energy for those bonds. So if you also notice there, the bond energy increases, as like I noticed, as like I said, as you go from single to double, triple, but also the wave numbers, the stretching frequency increases. It's the same thing. So if you need more energy input to cause a stretching frequency, that has a higher bond energy for that bond. So what we can use is basically, you can see graphically that if you hit a molecule with, let's say, 1200 wave numbers of IR radiation, and you get a specific absorption at that range, and your IR says, okay, some of this energy is lost because the molecule absorbed it, you can say that that's going to be a carbon-carbon single bond, pretty simply. And if you hit it again with, let's say, a 2200 wave numbers, and some of that energy absorbs, you can say, okay, we most likely have a carbon-carbon triple bond versus a carbon-carbon single bond. So by irradiating your sample with a whole broad spectrum of different IR frequencies, especially the ones we know about for sure, you're able to get specific functionalization and structural information for the molecules. So as we said earlier, IR induces molecular vibrations in covalent bonds. And using the ball and spring method is a great way to visualize this, even though that's not really, technically what happens. It's a lot more intricate than that. But the key thing is here, as we noticed on the last slide, it's very specific. These IR frequencies, stretching frequencies, bond energies, they have high levels of specificity, meaning you hit something with 1200 wave numbers of IR, it's always going to excite or vibrate the carbon-carbon single bonds. So the way to think about it is it's kind of like a fingerprint. If you hit a molecule, no matter what the molecule is, if you hit it with 1200 wave numbers of IR radiation, you're going to cause all of the carbon-carbon single bonds to vibrate at a specific vibration mode, and that will be printed out as the detector not seeing as much of that specific wavelength of IR come through and hit the detector after it's gone through your molecule. And so depending on how much versus your other wavelengths, you can tell how many carbon-carbon. Generally, you don't get a whole big readout on it, but it's you can see there's a lot of carbon-carbon single bonds. So you're able to hit things with specific frequencies to determine whether functional groups have it. Single versus double versus triple have their own thing. Carbon bound to an oxygen is different than carbon bound to a carbon. Carbon bound to hydrogen is different. Carbon bound to a nitrogen, it just keeps going on and on and on. So there's a whole big database of all this information you can look at and get a pretty good idea of what your molecule is just by looking at the IR spectrum from it. Now, you might have heard me talking about vibrational modes earlier. We'll go a little bit more into those. So vibration, of course, is what we're going to be talking about with IR. And covalent bonds have three main vibrational modes. Those are stretching, rocking, and a scissoring motion. Stretching is just that. If you move your arms away from and towards your body, that's consider your whole arm the bond. That's a stretching. It stretches out. Rocking is a bond, kind of. It's at a set point, like one of the atoms stays solid, doesn't move in space, and the other one moves up and down. So that bond is going to move up and down following that outer atom. That's considered rocking. And then when we're talking about scissoring, you've got multiple bonds going in the different directions or different up and down motions, and that's a scissoring technique. So in terms of IR, we're talking about stretching frequencies, and these are the most useful bands. Rocking and scissoring does have some stuff. They're more prone to other types, higher energy type things, Raman spectroscopy, something like that. But your standard IR is going to be using the stretching because that's the easiest to see and to use for normal detectors. So here's at the very bottom of the page here, we just got some very simple diagrams. Like I said, you've got symmetrical stretching where both of the atoms and bonds are stretching out at the same time. You've got something called asymmetrical where one's going in while the other one's going out. The scissoring is they're moving kind of in a almost a radial motion around, and you can have symmetrical and asymmetrical. But those are just basic, diagrams for you there. As we said kind of earlier when we were talking about the different types of radiation, IR is a lower energy, so it doesn't have enough energy to do any types of transitions with your electrons like you would normally see with UV. So we're only using IR. It's low energy, so it's very safe for your samples. It doesn't destroy your samples. And basically, as we say, we use a whole spectrum because we're looking for specific frequencies we're hitting your molecule with to induce these vibrational frequencies of the molecule. And that causes changes in the amplitude of vibration. It vibrates, the bonds vibrate more, and that can be seen as that specific wavelength of IR not transmitting fully to the detector. Some of it's absorbed by your molecules, and that's then redirected as an output in your graphic. So generally, when you're talking about IR spectra, you commonly see them as percent light transmitted to the sample. There are some where you can see absorptions as well. They have a different, one goes from the bottom up, one goes from the top down, which we'll talk about here when we start seeing these spectra. But if you absorb all light, for instance, in an absorption spectra, there's going to be a horizontal line near the bottom of the spectra. Transmittance, the full transmittance would be a horizontal line at the top of the spectra. So it's just depending on, when you look at the spectra readout, you have to see whether it's percent T or percent A for absorptions or transmission. And one's going to be coming from the top down, and the other one's coming from the bottom up. And just some basics about the actual instrument itself and the process it goes through. It's pretty simple, actually. You just have a little holder for your sample, whether it's in a sieve where it's trapped in like a potassium bromide pellet, or a lot of the newer molecules just have basically a diamond crystal that you can put solids or liquids on top of and compress, and then the IR is transferred through the crystal, hits your molecule, bounces around, and how many bounces it is and the change in the frequencies can also be used to do. It's called an ATR system, and most of your more modern benchtop infrareds have that system, so you're able to do solids and liquids really quickly without having to use a pellet or anything special. But basically, you have a sample holder where your sample is, and your IR source will irradiate that sample. And on the other side of your sample from the IR source is your detector. And like I said, if your IR passes through your sample and isn't absorbed, it's fully transmitted, hits the detector. If the IR frequencies hit your molecule and start inducing vibrations, not all of that IR is going to be passed through. Some of it's going to be absorbed by your sample, so the detector sees less than was initially transmitted and basically marks that down. And when it spits out your little spectrum, it shows, hey, less of these specific frequencies were transmitted. Here's a graph of that. You can see what's in your molecule. Here's just a really simple diagram of what an absorption mode IR spectra would show for a very narrow range of the wave numbers, 3600 for specifically. If you notice at the bottom, it's got wavy. There's always going to be noise because even near 0 degrees Kelvin, which you're not going to ever make in a lab, there's some rotation and vibration of molecules just from room temperature or anything like that. So it's always going to be a jagged, kind of noisy line. But at the bottom, you can pretty see that most of the molecule is 0 or close to it. And then you got a really big sharp spike right at 3600. So that's basically showing you that near 100% absorption was determined at the 3600 wave numbers of IR irradiation. So that whatever the 3600 is, that molecule is pretty much that functional group is pretty much guaranteed to be in your molecule. And so that's just a simple way of looking at it. When you see an actual IR readout, it's a lot more messy, a lot more involved, but this is, baby steps for now. Here we have the exact same readout, but this is in transmission mode. And for chemistry, this is generally what all of your IR spectrum are going to be in, is transmission mode. This is the standardized version of what most ACS and chemical readouts use for IR. And it's, if you notice, they're the exact same. It's just top down or bottom up. And transmission and absorption are inverses. So it's, if you have 100% absorption, you have 0% transmission, vice versa. It's the same thing. So they're the exact same. They're telling you the exact same thing. They're just using different standards of doing it, is really all the way you can look at it. Now, when we're looking at IR bands on an IR spectrum, that's what they're called, the peaks and valleys, all their bands, basically. There's some classifications you need to know about. And in terms of the actual peaks, weak, medium, and strong. Weak is just going to be a small peak, very narrow. Medium is also going to be a narrow peak, but it's, basically, anywhere from, say, like 30 to 70% transmission in this circumstance. And then strong is a very deep peak that goes near 100%, but it's basically greater than 75% absorption or transmission, depending on which graph you're looking at. But those are the key things: is strong, medium, and weak. And you're able to tell specific things. Like, you might have a vibration at 1600 nanometers that, if it's a weak vibration, it'll be a specific functional group. But if it's strong, it's a different functional group. So it's easy to get confused. That's why a lot of these IRs are directly hooked up to internet databases, where it can just take what its readout, compare it to what's out there, and give you a percentage. Hey, it's 98% equivalent to this, so most likely that's what it is. Unfortunately, you won't be having those readouts. You'll have to be, using basically charts in a book and some basic information to determine some IR spectra. But, we give you easy stuff, hopefully, for the quizzes. I hope at least Dr. Mighty will. Now, the key thing to think about here is we're talking about vibrational modes and covalent bonds. But the caveat is not all covalent bonds will display on an IR spectrum. For instance, if you just have just a very simple carbon-carbon bond with nothing attached to the carbons, of course this can't be. This is just a hypothetical. But if it's just carbon and carbon with a single bond, that actually will not display on the IR spectrum. There has to be other things attached to those carbons, because basically, like we said, the reduced mass. So the mass of what's attached to each of these balls on the ball and spring model plays a huge importance in the vibration. So if it's a symmetric molecule and it's exactly the same, they're not going to be an IR active vibration. So you have to have a polarity difference. It can be a true polar bond, or it can be a induced dipole where there's a temporary polarity system, but there has to be some type of polarity. We've got some examples down at the very bottom. Far left, the carbonyl, the carbon double bond to an oxygen. That double bond to oxygen, that's a very polar bond, carbon versus the oxygen. So that's highly IR active, and it's got a very, very sharp peak, very easy to see. Your carbon nitrogen, triple, even though it's triple bond, it's a strong bond, but there's an electronegativity difference between carbon and nitrogen, especially with the lone pair of electrons of that nitrogen. So that's an IR active bond. But not as much as the carbon oxygen. So it would be a medium peak. It wouldn't be, the 100%. It'd be, around 50, somewhere in that range. Now, in terms of a weak, we've got, for instance, there's the carbon-carbon triple bond. Now, it is just carbon bound to carbon, but the carbon on the left has a hydrogen bound to it, while the carbon on the right has a methyl group bound to it. So there's a difference in mass of the overall system. So it's a slightly different polar environment from one side to the other. So that's why it's considered a weak peak. Now, if you look at the very last molecule, we've got the dimethylacetylene there, and it's a carbon-carbon triple bond, but it's a symmetrical model. If you put a line right down the middle of that triple bond, both sides are exactly the same. So there's no reduced mass. It's all exactly the same. So no matter how much those molecules vibrate, the molecule looks exactly the same. It's just more stretched out. So if you have a symmetrical molecule and everything's the same on both sides, you're not going to get an IR active band. And I can pretty much guarantee you're going to have at least one question like that in one of these quizzes here. So if you see a symmetrical molecule, even if all the bonds are covalent in that molecule, it will not be IR active. That's the main thing to remember out of this. Now, in addition to the weak, medium, and sharp or strong peaks, we also have narrow or broad peaks. If the specific IR absorption or transmission is targeted to a function group like a carbon bounded to oxygen or carbon bounded to nitrogen, those generally are going to be sharp peaks. They're very specific. But if we get into things like a hydroxyl group, an OH bond, especially things that can hydrogen bond, then your peaks start to broaden out. Because when things are hydrogen bonding, they're doing it millions, if not billions of times a second, and they're just bonding to other things around them. So while everything is stretching at that frequency, it's kind of smeared out because things are coming off of each other and, attaching to different molecules. So it's a big smear. You see this also in NMR as well. So the key thing to think about here is when things can hydrogen bond, you're going to have peaks that are broad. You see this, like I said, in alcohols, carboxylic acids. You see it a little bit in some ethers and esters, stuff like that. But mainly the hydrogen bonding, you'll start seeing these broadening of peaks. It's very indicative when you have a carboxylic acid or an alcohol. Now, as you said, IR is really, really good for determining either the presence or absence of specific functional groups. Like, do you have a carbonyl? Do you have an amine group? Do you have a hydroxyl? Do you have a carboxylic acid? Stuff like that. It's really, really good at determining that. It's like I said, these are very specific frequencies, and so this can give you almost a molecular fingerprint when you're comparing your sample. Like if you're wanting to synthesize something, and you did everything, you did all the steps you're supposed to do. Now, is this molecule what you think it is? So a quick and cheap way to do it is stick it in the IR, look for all your specific functional groups that are supposed to be there, and compare it to either a known sample or what you think you should have, and you can get a percentage of variance and see how close it is. That's a good way to do it. What IR does not do, however, is give you proof of that formulary structure. It can say there are some of these stretches and bonds in there, but you might have multiples of them. They might not be in the right place. It doesn't give you information on fragmentation or where functional groups are located in the specific molecule. All it says is you have these functional groups somewhere. So IR is great. It's just a quick, cheap way of doing things, but it's not the end all. You can't just take an IR of a synthesized compound and go, this is this, I know it 100%. You have to have additional supplemental information, stuff like either additional UV, or you can do qualitative stuff, or NMR, or mass spec, or if you're doing any type of research or publication, all of the above, just because you want as much information to prove you have what you have. So IR is very powerful and it's really helpful, but it's pretty limited in scope. You've got to use it in conjunction with other techniques. Now, one unique thing that IR spectrums have is something called a fingerprint region. Now, this is anywhere from around 1500 to 400 wave numbers. And these IR frequencies are kind of to the point where they will vibrate the entire molecule as a whole. And instead of specifically activating, a carbonyl bond or a CO stretch or a CH stretch or a triple bond, stuff like that, the fingerprint region of energy basically just vibrates the entire molecule as a whole. And since all molecules are inherently different, this is called the fingerprint region, because if you vibrate, say, acetone in that frequency versus, dimethyl ketone, you're going to have different fingerprint regions. They're going to have a specific thing. It's going to be the same way every single time, because that molecule, based on its shape and its center of mass and the atoms connected, is going to vibrate the same way every time, whereas the different molecule will vibrate differently. So even if molecules have the same functional groups, but they're different in mass, they're different in shape, their fingerprint region will be able to help you a little bit more. And unfortunately, the fingerprint regions are so messy and convoluted that generally humans can't pull too much out of it. That's where we get computers and statistical methods and models. So that's where these databases come into. They take all of your functional group information into account with the fingerprint region and give you a broader idea of what you might have. And that's what, if you use an IR that's connected to a database, when you scan your sample, it'll give you a printout of like the 5 closest percentage-based molecules to what you have and what's close for database matching, a lot of these statistical techniques. But if you're looking for something specific and you're targeting something and you think you might have it, that's a good way of getting a pretty good idea of what things are. All right, now we're going to start looking at some actual IR readouts, transmission mode readouts. Here we have a readout for 1-butanol. So for this specific molecule, we were talking about the fingerprint region, and that's from 14 to 6 or 14 to 5 in that range. Basically, it's all relative to the quality of the machine you use. Some will have a longer range, some will read out less, and you can dial it in when you make your own readings and stuff like that. But the fingerprint region is that region on the right, and that region from 1400 in this case to 600 is going to be really specifically tuned to that specific molecule. So even if you do another molecule that's similar to 1-butanol, it's an alcohol, it'll have similar, it's like 1-propanol instead. That you will see the same the OH stretch and saturated hydrocarbon stretch on the left for both molecules. They'll look basically the same, but the little fingerprint region on the right will be completely different, and that's how you can differentiate it. So this is just a way of looking at it. So like this says here, as a student, you really should be focusing on the left part, the not fingerprint. Basically anything over 1400 wave numbers is what you're going to be focusing on. The fingerprint region is just all convoluted. There's tons of stuff overlapping in there, and you won't really be able to differentiate anything. Okay, now we come to actual absorption ranges for specific bond types, which is going to be really useful when you're trying to determine this, a readout and what it is. So for covalent bonds, generally the range you're looking at is 600, which is about 500, 600 is about the bottom of that fingerprint region, to around 4,000 wave numbers, and that's going to be the main output of your standard IR. Anything below that, below the 600, is just either too low level of vibrational modes or it's just too convoluted to tell. Anything above that is getting very, very close to visible range, and that's a different type of excitation than IR. So these are very hard to memorize. If you are a chemist or a materials physicist who uses this stuff, you'll know specific things just from using that type of chemical over and over again. But there's so many different types of functionalization groups and bond types that it's really, really hard to get all this stuff down, especially in a short class like this. So what you'll mainly be using is either online printouts or databases that give you absorption range charts like this. So like for instance in this one you can see kind of in the middle the brighter green. In that range from say 1600 to a little bit over 1800, about 1850 or so. In that range, if you get any absorption or transmittant peaks in there, it's either going to be a carbon-carbon double bond, carbon-oxygen double bond, or carbon-nitrogen double bond. If you get anything that's around 2500 2250 in that range, it's going to be a triple bond with either carbon or nitrogen. And then if you start getting towards 3000, 3500, it's going to be a single bond. And then the higher the wave number, the differences are going to be either the carbon hydrogen bond, oxygen hydrogen bond, or nitrogen hydrogen bond. And then if I also notice where the convolution gets in the fingerprint region, you also have specific wave excitation, vibrational excitations for your carbon-carbon bonds, carbon-oxygen, carbon-nitrogen, carbon-hydrogen, that are all in that fingerprint region. So that's why we generally don't look at that. We let the computers deal with that. It's just too much information going in there. All right. Now, we'll go over some basics of alkanes versus alkenes versus alkynes. Here we have normal hexane, just a 6-carbon chain with methyl groups at the end terminating. And it's all alkanes. It's just very simple carbon-carbon single bonds with hydrogens in this case. And so there's technically no functional groups. It's just all carbons and hydrogens. That's special. So when you do this IR, you're really only going to see a carbon-carbon double bond peaks and carbon-hydrogen bond vibrations. That's really it. So one of the more common things you're going to be looking at when you do any IR is around 3000 wave numbers is your standard area for a carbon-hydrogen single bond stretch. And if you notice here, right around 3000, a little bit less actually, you have a very, very high transmittance of, very, very low transmittance or high absorption of that. So basically what that's saying is we irradiated your molecule in that specific wavelength, and we've got a sharp peak with some little peaks and valleys in it, meaning you have a bunch of different environments of the carbon-hydrogen stretch, and those are all going to account for the carbon-hydrogen bonds in the hexane. Now, if you notice, you really can't tell anything from there on how many you have, how many methyls versus methylenes versus carbons that just has one hydrogen. You can't tell. All you can tell is you have a prevalence of carbon-hydrogen single bond stretching right there at that frequency. So generally, any organic molecule you have is going to have some carbon and hydrogen single bonds in it. So that's a very key thing you can look at. If you don't see those, most likely you're not working with an organic compound. Also, if you notice around 15 to 1400, there's also some CH in there as well. That's the carbon-hydrogen bending where the bond bends. And that's starting to approach into that fingerprint region. The about 1570, 1580, that CH bend is still usable as a investigative tool. And that just gives you more knowledge saying that there are carbon-hydrogen single bonds in your molecule. Now moving on to alkenes, having a carbon-carbon double bond in the molecule. It's still an organic molecule with carbon and hydrogen in it, so you're still going to see those a little bit less than 3000 wave numbers. You're going to see that carbon-hydrogen stretch, and that's a carbon-hydrogen alkane stretch. That's still there. You still see the carbon single bond to hydrogen bending at around 1475, 1480. That's still there as well. What's new here, you have two extra things. Mainly, the carbon-carbon double bond stretch is around 1640, and it's a very sharp peak. It's not broad at all because it's a very specific. That's a specific type of bond in very localized area, so that's going to be there almost every time. And then also you have at 3080, it's different. You have a carbon single bond hydrogen stretch, but if you notice, this is the carbon that has this is an sp2 carbon. It's got a double bond on it. So it's that double bond, the alkene part. And that's slightly more energy. It's higher in wave number because of that double bond. It's a stronger bond, and there's more mass associated on that other side than there's with the hydrogen. So it's going to take more energy for that to happen. So even though it is a carbon-hydrogen stretch, it's a carbon associated with a double bond. So it's a little bit higher in wave number. So you can tell right off the bat, if you've got the little broad offshoot above 3000, you're going to have a carbon-carbon double bond in there. If you also have around 1640, that carbon-carbon sharp peak. Now here's something that can happen quite a bit, happens all the time, is if you have a bunch of carbon-hydrogen there, you can actually obscure kind of that carbon-hydrogen double bond associated stretch at a little bit over 3000. If you notice here, you do see the around 1650 to 1680, that carbon-carbon stretch. You just see a high prevalence of carbon-hydrogen alkane stretches, but you've got a tiny little bump there at the end above 3000. It's easier to see in this because we wanted to show it to you, but in actuality, when you take, sometimes this will be a lot more, that around 3000 range will be a lot more broad, and you won't have an actual offshoot with a peak in a valley that you can see. It'll be kind of convoluted into there and hard to see to get out. So the key thing to look for is really around that 1650 to 1680 in that range. If you see a sharp peak there, that's a very narrow peak. It doesn't have to be strong, doesn't have to be high absorbance, but if you see a peak in there and then you see something, even if it's smudged or broad over 3,000, you know you're going to have a carbon-carbon double bond. Okay, now when dealing with alkynes, the carbon-carbon triple bond, it's going to have a prominent sharp peak around 2100 wave numbers. We'll show it to you here in a second, but it's a weak band. And it's weak because when you're dealing with triple bonds are not very polar. They don't like to be stretched or bent very much. They're very linear in nature. They're very strong, hard to break apart, very stable bonds. That's why it's a very weak bond, even though whatever might be attached to the other sides of those carbons might be polar in nature and very easy. The bond itself is fairly nonpolar. And also, like this says here, if you have a fairly symmetrical alkane, you might not even see it at all because of the low polarity. And in addition to the symmetry, when they start to vibrate, there's not much difference. So the main difference is if you have a terminal alkene, where one of those carbons is at the end of the molecule and there's nothing else, or just hydrogen. Therefore, it's just a standard sp carbon. Now these also have a sharp weak band because it is still a triple bond, so it's very nonpolar. But this is going to be around 3,300 wave numbers, and that's in the CH stretch range. So the 3,300 is going to be a CH stretch associated with a triple bond or an alkyne. So you've got a little less than 3,000 is carbon hydrogen alkane. A little bit over 3,000 is carbon hydrogen alkene. And then 3,300, so a little higher, is corresponding to the carbon-hydrogen stretch for alkynes, the triple bonds. Now, if you have an internal alkene where it's kind of in the middle of the molecule, and there's no hydrogens on these carbons, they're just pure sp, you're not going to see that band. You're not going to see that 3,300. So you can tell the difference between a terminal and an internal alkyne directly from an IR. You can see that. So we've got a couple different versions on slides coming up, so you can see it for yourself. All right, here we got the two different slides for you, two different IR readouts. The top one is 1-octyne, and the bottom one is 4-octyne. So the 1-octyne is a terminal alkyne, while the 4-octene is an internal symmetrical alkyne. And if you notice right off the bat, on the top for your terminal alkyne, you see a 21, around 2120 is a stretch for your carbon-carbon triple bond, and it's fairly weak, but it's sharp, so it tells you very specific for that. And then you also see around 3,300 the carbon-hydrogen triple bond associated stretch. So that tells you, and it is a very sharp peak. It tells you very distinctly that you have a triple bond, and it is terminal. Now, if you look at the very center, the bottom molecule, that the alkyne is center, and it's a pretty symmetrical molecule, so you actually don't even see the 2200-ish carbon-carbon stretch, and you don't see at all the peak in the 3300s because there is no carbon-hydrogen. So you would look at that, and you might even think, hey, it's just hydrocarbons with alkane with no bonds, but it actually is. It's just because of the symmetrical nature of the molecule and the fact that the triple bond is nonpolar, sometimes it can be very hard to see. Moving on now to IR of a nitrile. Nitriles are carbon triple bond to a nitrogen. So again, talking kind of like what we do with the carbon-carbon triple bond, but this one's a little different because we do have polarity. Even though the triple bond is a nonpolar bond, when you have two different electronegativities in the atoms associated with those triple bonds, it becomes a polar bond. So it's very similar. You're going to get the same around 2200 stretch, but this is going to be a lot more prominent, and it's bigger of a transmittance or absorption, depending on how you look at it, because of the fact that it is an actual polar covalent bond. So that's another way to look. If you see that in that range and it's a pretty deep peak but sharp, then you can know it's going to be a carbon-nitrogen nitrile versus a alkyne. Here we have a spectrum of an alcohol again, 1-butanol, like we showed a little bit earlier. So we have a bunch of sp3 carbons, carbon single bond to a hydrogen in alkane form. So we're going to have a bunch of the saturated CH stretches a little bit less than 3,000. And then if you notice around 3,200, 3,300 in that range, we have a really broad peak. And that anytime you see those really, really broad peaks like that, that is very indicative of an OH bond. And like I said, that's because of the hydrogen bonding. The hydrogen is coming on and off of different molecules and kind of spearing everything in that area. So anytime you see an IR that has that really broad peak in that, between 32 to 3,500, that range generally, sometimes they go a little bit higher than that, but that area is very indicative of a OH. Now, it can be an alcohol. It can also be a carboxylic acid. If it was a carboxylic acid, since carboxylic acids also have a carbonyl, a carbon double bond to an oxygen, you would look for a specific peak for that as well. So if you saw that broad trough there around 3,300-ish, and then you saw another peak a little bit further up in wave numbers, then you could say it's carboxylic versus alcohol. And I'm pretty sure we're going to come up to that next. So for carbonyl compounds, anything that has the carbon double bond and oxygen functional group, we're talking about aldehydes, ketones, carboxylic acids. A little different. If we have the key thing to think about here is like with an aldehyde, the carbonyl group is at the end of the chain. Ketone, it's somewhere in the middle of the chain. So therefore, because of that, just kind of like we had with the terminal and internal triple bonds, it's going to be the same thing. You can have different areas of peaks. So if you have a carbonyl and an aldehyde, you'll have a different peak than a carbonyl and a ketone versus a carbonyl and a carboxylic acid. So these carbonyls show very strong, prominent bands, and it's around 1720. That's the main thing with those. They don't move very much, and it's kind of right in the middle of the spectrum, so it's pretty easy to see. And it's very sharp because it's a very polar bond. And like I said, it's because of it's right in the middle of your screen. It's very sharp. It's a really deep, strong bond. It's hard to miss, so you'll know basically immediately whether or not you have a carbonyl in your molecule. So you're also going to see something like with an aldehyde, you've got a carbon-hydrogen bond, but that carbon is actually an sp2 carbon because it's got that double bond to the oxygen. It's not an sp3 carbon. Because of that, you're also going to see some medium bands around 2750 or so. That's going to tell you the difference between a carbonyl and an aldehyde versus a carbonyl and a ketone. If you see those bands around the 2750, 2800, that range, that's going to be an aldehyde. If you have a ketone, because it doesn't have, it's internal and it doesn't have that terminal carbon hydrogen, you're not going to see those bands. So that's the way to be able to tell. And just like we did before, the next slide coming up will show you the difference between the two. Here we have the representation of an aldehyde versus a ketone in IR. Your top slide is butyrollaldehyde, and your bottom slide is 2-heptanone. So your top slide is your aldehyde. It's got the terminal carbonyl with the sp2 bond carbon hydrogen. And the bottom is your ketone. It's got the internal carbonyl, and it doesn't have an sp2 hydrogen bond to that carbon. So if you notice, they both have right in the center of your screen that huge spike right there. That's your carbonyl. Like I said, it's hard to miss. It's right in the center, right there. Now, what you're looking for is they both have carbon hydrogen bonds. So in less than 3,000, you're going to get all those convoluted peaks for carbon hydrogen. But that 2750 to 2800 range, that's the different thing. On the bottom, you don't see that at all. On the top, you see those two peaks in that area. So that would tell you right off the bat, you have a carbonyl because of the big peak in the middle, and you have a terminal sp2 carbon bound to a hydrogen because of those 2800 or 2750 range, whereas the bottom one doesn't. And that's how you would be able to differentiate between a ketone versus an aldehyde on IR. Okay, now we're moving on. Talked about ketones and aldehydes, so now we have to move on to carboxylic acids. Carboxylic acid has a carbonyl in it, the CO stretch. So you notice from this IR, right in the center, you got that huge carbonyl stretch around 1720 or so. So that's easy to pick out. But when you look over to the around 3,000 range with the carbon hydrogen range, it's all broad and stretched out. So the first thing you should think is it's broad and stretched out, so there's probably an OH in there. Very good guess. But if you notice, it's broadened and stretched out way further down than just a pure OH. It's kind of all convoluted into that area. And because of that, that whole broadening and messing up of that range from anywhere from like 3,500 to 2,700, 2,800, anytime you see that and you also see that carbonyl stretch, that tells you right off the bat that it's the carboxylic acid. And again, it's the same reason as with the alcohol. Because of that hydrogen bonding, and then you've got that extra polarity of the carbonyl, that hydrogen can just basically abstract itself, move around all over the place. So that causes that huge OH stretch to just go everywhere. And that's it. Carboxylic acids are one of the easiest things to see. When you see an IR that looks like this, you don't even have to think. It's like huge CO spike, broad OH spectrum that mixes with the carbon hydrogen single bonds. Bang, you got a carboxylic acid. Simple, done. Now, moving on a little bit more to other things you might see fairly prevalently in organic molecules, are amines, the sp2 nitrogen hydrogen bonds. And the characteristic thing to look for here is the NH bond stretch itself. So the NH bonds they're polar, so they're going to show up, but they're kind of medium to weak, and they're kind of broad as well, because remember, hydrogen bonding can also occur with nitrogen bound to hydrogen as well as oxygen and fluorine. So that's why you're going to have the broadening as well. It just keeps happening, trends over and over and over again. But it's not as broad as oxygen to hydrogen, because that's more of a polar bond and a lot stronger in terms of what it can do. But the thing to look at is this kind of weak, broad spike around 35, 34, in that range. So it's going to be around the same area as your OH bonds, but it's a lot weaker, and it's not nearly as broad. So here we show on the dipropylamine. It's a terminal amine. You see the CH stretches there, a little bit above, a little bit below 3,000. But then around, say 3,300, 3,400, you see that tiny little peak, and it's kind of broadened out in that area. So that's very indicative of a sp2 nitrogen hydrogen stretch. Now, in addition to the nitriles, the carbon triple bond nitrogen, the amines, the nitrogen hydrogen stretches, we also could have amides, which are or amide, you might hear both ways. That's a very common organic molecule. It's in biochemistry as well. It's building block molecules. That's a carbonyl that has a NH2 group, or a nitrogen having group attached to it. And that carbon is an sp2 carbon that has the carbonyl, the nitrogen attached to it. That's one of the key things. So again, because we have with the amides, we have a carbonyl, you're going to have that indicative right around 1700, huge stretch right down the middle. So you see that right off the bat. So okay, there's carbonyl. But then we also have that terminal NH2. And just like before, it's going to be a broad peak, but because this is an incredibly polar molecule, there's hydrogen bonding acquired, it's going to be a lot stronger in this case because of the presence of that carbonyl. So it works the same exact way as the OH and the carboxylic acid. The difference here is, if you notice, the peak is a little bit further upfield than it is with the OH, and it doesn't have the full broadening effect where it encompasses the CH stretches. So that's a way where you can tell the difference between a carboxylic acid and an amide. The stretching, broadening from the NH will not fully encompass the CH stretches a little bit below 3,000. So that's the two different key things there.